Good morning, everybody. Today we'll study data structures and algorithms related to physical design automation. I'll first start with the basic VLSI design cycle. So it starts with the system specification in which we formally define the problem. We define the properties that the inputs and the outputs should have. So, and also the ordering of the outputs. Then we come to architectural design, where we design the complete architecture of the circuit, right? So what will be the different components of the complete application, how will they communicate and all. In the functional design part, we define two things, the data path and the control logic. So we define the number of registers and what will be the functional units, and also the control flow through the registers and the functional units, and also the control of the complete application. So from there we come to logic design, where we transform this, both the control logic and the data path, into a set of Boolean equations. In the circuit design phase, what we do is we transform it into at the gate level and up to the transistor level. So performance, power, etc. are considered, and in physical design we have the circuit in the form of a set of nodes and the net list. So what is a net? It is an electrical wire, you can say, connecting the different components. So it can be one wire which is connecting, say, 3 components, right? So a list of nets is given and the output is a layout, a geometrical layout on the floor. So each in that geometrical layout there will be blocks which will define components and the interconnection between the blocks. So that layout, that netlist is transformed into a layout. In the fabrication, what happens? So in fabrication we take this layout and put it on a wafer and make that we actually make it in hardware, and then in packaging, testing, debugging, we package it and test for its correctness and debug, right? So the physical design process, the process of converting a specification of an electrical circuit in the form of a netlist, which I just defined, into a geometrical representation called layout, right? So it looks like this, and it deals. What is physical design automation? It is the research and development of algorithms and data structures related to physical design. As because this is a very big optimization problem, we divide it into separate parts and try to solve it. So we first partition it into sub-circuits so that each of these sub-circuits is controllable, and then we find out where will this be placed so that the interconnection length is minimized, and then we find out the channels through which the interconnections will actually take place between the blocks, and then we try to compact the whole area of the total system, right? So therefore this is the different stages of physical design. Partitioning, we partition it, right? So you see this A part of this figure. So this A part of this figure, it divides this into 3 partitions, this circuit into 3 partitions, and then individually tackles the problem of generating layout of each of these 3 partitions and the interconnections between these partitions. So floor planning and placement, what that does is, given this partition, the blocks, the number of terminals in each of these blocks, the different connections between each of these blocks, where should these blocks be placed, right? So this is the where should these blocks be placed so that the interconnection length is minimized and the total area of the chip is minimized, and also timing constraints. Maybe the interconnection length is so big that a critical net fails to meet the timing constraints, that the signal must pass between these 2 components within a specified time, and we are not being able to meet that. So those considerations need also to be seen. In routing, there are actually 2 phases, global and local. In the global routing phase, what we do is we list out different channels and things called switch boxes, which we'll take in the second part of this course, and find out the connections. So between two blocks, say there is a layout which contains two blocks at different places. So we find out the different channels and switch boxes through which these connections will be made, right? And in the local routing phase, we take each channel and or a switch box and make the connections. So in the first part, our objective is to minimize the number of channels, maybe the total length of the wires, and in the second part we have to say then we can say that there is a channel and we have a block up and below. We can say that we want to minimize the number of bends, right? So the objectives are different. So in a channel routing at the local phase, we know what will be the number of wires which will be passing through and which will be connecting the up and below blocks, right? So our objectives are different. In the compaction phase, we want to minimize the complete area, right? So as because time to market, cost, etc. determine this design, physical design, we have different styles of design. We have full custom design, standard cell design, gate array design, FPGA design. So in full custom design, what will be? It's like generating a complete complex processor like the Pentium. So we have the time to market is large, and the cost of generation, cost of design is also huge, but the system needs to be perfect. So we have to be able to maneuver even to the individual transistors for performance and everything, right? So this, because once this thing is made, once this design is made, we'll make crores of such chips, right? But in the case of an ASIC, say, which will be planted in a toy, we need not do such a thing. We need not make such complex performance optimizations in terms of area, power, etc., right? So there we can say that something sort of this satisfies what? Standard cell design, where I know where I have a library of cells which is prefabricated and pre-designed. We know the layout of each of these cells. We only put the cells and the interconnection between the cells, right? So we have a library of cells and we do not go into what within this layout, right? Within the layout of these cells. And then we have the gate array style design. What we have in this, so in that standard cell design, the cells were standard, but within the cells any type of a layout can be generated. Here this is this gate array, in this gate array style design, what we have is, we have a board which is composed of an array of gates only and nothing else, and we group gates to generate these cells. Of these standard cells, we group gates. So we don't even generate the layout of those standard cells also, that is also standardized here, right? And in the FPGA, the gates, the cells are also given, the interconnections are also given, we only need to program the interconnects, right? Okay. So if we compare the different design styles here, in a full custom design, the cell size is variable, the cell type is variable, so any cell type can be generated, cell placement is variable, interconnections are variable, fabrication can be done in different layers, and the area is very compact, right? In the standard cell, the cell height is fixed, the cell type is variable, so we put the cells in different rows. Because the cell height, we have rows and we put the cells in different rows. Interconnections are variable, fabrication can be done in all layers, and it will be worse with respect to full custom design, obviously. In the gate array, cell size, cell type, placement are all fixed, interconnections are variable. So we can actually generate the different interconnections, we'll route it, right? And for an FPGA, even that is done, the interconnections are done, we need to actually burn fuses or not, we need to program it, okay. right? We don't go into sea of gates. So in terms of performance, design cost, time to market, full custom design, in all these aspects is high. In standard cell design it's moderate, gate array is still moderate, FPGA is low. So right. So now we come to the representation of a layout. So we'll first go into the data structures that represent a layout, and then we'll go into algorithms, right? So what's a layout editor? It's sort of a drawing tool for the VLSI design process. So we need to maneuver the different components and find out the best design, right? So a layout here is considered to be composed of a set of tiles. So a tile is a rectangular section, and two tiles will not be allowed to overlap, obviously, because they are components. If it is a component which contains a circuit, we'll call it a block. If it is a vacant area, we'll say that the tile is a vacant tile or a vacant space, right? So rather, the vacant space is also divided into a set of tiles for our convenience, right? So different layout examples can be here in the above diagram. A, B, C are different blocks, and the rest is different vacant space. The rest is a vacant space. And in the diagram below, we have also divided the vacant space into vacant tiles. How? We have tried to find out maximal horizontal vacant strips, right? So you see, we have tried to cut the whole design into maximal horizontal vacant strips and try to generate vacant tiles, right? Okay. So these layouts are generally represented in some linked format. So blocks will be linked and will maneuver with this linked list to get through, right? So we'll see one type of data structure here, corner stitching. We'll go to this after this. So first we come to what are the different atomic operations that is needed so that we can maneuver with the blocks. What can be the different types of operations that may be needed? See, first is point finding. I am given a point and I need to find out whether point P lies within a block, and if it lies within a block, then I have to find that point. So in a block means, is there a component or a vacant space? I want to find out whether that point contains a component or a vacant space, right? Neighbor finding. Given a block, I need to find out all the blocks which are neighbors to this block. Block visibility. So determine all blocks which are visible in the x and y direction. So do I have a series of vacant tiles between two components? So can this block see this block? Then it's easily routable. I can just put a straight wire and route this to interconnect these two blocks. Area search. So given an area, given by its left corner, x and y coordinates, its width and its length, we determine the blocks which intersect with this area A, right? So what may be the reasons? Maybe I have an area and I want to place a block in that area. So I first need to find out what are the blocks that are intersecting, right? Then I need to somehow move those blocks, make that free space and put a block in that area. So this is why it's required. Then directed area enumeration. Given a fixed area A, visit each block intersecting A exactly once in a sorted order. Block insertion. I want to insert a block such that it does not intersect with any existing block. Block deletion, again, I want to remove a block from the layout. Plowing. Given an area A and a direction D, we need to remove blocks Bi from A by shifting them in direction D while preserving their order. Why? Because if I don't preserve their order, I may not be able to interconnect that, right? So considering routing considerations and everything, if I have to place a block at a particular area, I'll remove the blocks from a particular area. I remove the blocks from a particular area in a given direction, keeping their order, and then place my block over there. Okay. Block insertion. Insert a new block B. Oh, block deletion plowing was done. Sorry, compaction. Compaction. So we need to compress the entire layout, right? And channel generation, determining vacant space in the layout and partitioning it into tiles. Okay. So now we come to the corner stitching data structure. A floor with some solid tiles are given. Partition the floor into maximal horizontal strips to define either block tiles or vacant tiles, right? For each tile, store its position, size description and other attributes. Insert corner stitches, that means 4 pointers pointing to appropriate neighbor tiles. So here we have the RT pointer, which right top, which points up, the top right, which points to the right, the bottom left points to the left, and the left bottom points below, right? And example, how corner stitch data structure joins all the blocks together. The right one, the right example, right? Okay. So we'll now see one example with the corner stitching data structure. So given a point P2, find a path through the corner stitches from the current point P1 to P2, traversing the minimum number of tiles, right? So what is the idea? The idea is simple. So we will first go through the right top, above or below, right, to find out the block in which the point, my target point, is there, right. So here, say from this source, we want to find this destination point D here, right. So we move up and then find out the block which contains the destination point. Okay. Then we move left. See, we come to the algorithm. Move up or down using the RT or LB pointers using a tile until a tile is found whose vertical range contains the destination point. Now we move left or right using the TR or BL pointers until a tile whose horizontal range contains the point, right. Whenever there is a misalignment, so what is a misalignment here? If we come here, a misalignment, whenever we come to the tile just to the right of this, we find a misalignment. Okay, okay. So is it visible to you? Okay, fine, thank you. So when we come to this block, we have a misalignment. That means, sorry, we come to this block, there is a misalignment. That means this its horizontal or vertical range does not contain the destination point. So we again go to top. See here, we find out the vertical or horizontal. We go up until the vertical range contains the point. Then we move left. When we come to this tile, we were moving left, but we find that its vertical range, its vertical range does not contain, the horizontal range does not contain this tile. So we again move up. So if there is a misalignment, we go to again steps 1 and 2. So by repeating this, we find out the destination point. Is it clear? Right. See, it can be for various reasons, but I have a destination point within the given board of the layout in my drawing board, and I want to find whether that point contains a vacant tile or a block tile. So when I have reached that point, what does it mean? I have reached the block that contains the point, right? So when I have reached that block, I know whether it's a vacant tile or a block tile, correct? Right. Finally, again, okay. So another can be finding the neighbors of a tile. So given a block, I want to find its neighbors. How can I do so? I can just go to the top right, and find out there is a block, and then I go series through the bottom pointers and find out all the blocks. Say I want to do an area search given an area. So I don't have there are algorithms for all this. I don't, because of the paucity of time, I won't go into all the algorithms, but say I have an area search. What will I do? So for this area, I'll find out, first I'll find out the block which contains its left point. So in that area search, what we need to do, we need to find out whether there is a block tile that intersects with that area or not, right? So first we'll find out the left point, the x and y coordinates, the block which contains the left point of this area. If this is a vacant tile, then we'll see its right edge of this vacant tile. If the right edge of this vacant tile is within the right edge of the area, then we can say there is a block tile that intersects this. Why? Because we have maximally horizontal strips. So if I have, if the right pointer to this vacant tile contains a block tile and the right edge is within the area of the area under consideration, then I can say that a block intersects through this area. Yes.
Say we have a block to the right of the vacant tile.
Right.
But that doesn't imply that that block will be within the area that we are considering.
Yeah.
It can be small, this side can be small.
Yes. Yes. So I have an area. Oh, if that is so, yes, you are correct. If that is so, then we'll also have to find out. We will go through the next step. So we'll find out whether there is a on the right or on the left or not. We'll find out. See, we have an area and we have a top edge also. We know what is the coordinates of the top edge. So we'll use that also under consideration at that time. So next we come to algorithms. First is partitioning. So what I said is, partitioning is decomposition of the complete system into subcircuits, which can be designed independently and concurrently with the other blocks. So we want to simplify, I want to simplify my design process. So input is a set of components and a netlist. So what is the netlist? I told you. So in the form of a weighted graph or hypergraph, the nodes representing modules and a edge or hyperedge representing a net. So what is a hypergraph? So hypergraph is a set of vertices and the edges are also subsets of from the set of vertices. For example, say I want to define a net. A net may not be just connecting two components. A net can be connecting numerous components. So if I want to, so if a net represents a connection between component number 1 and component number 4, so 1, 2, 3, 4, if it wants to represent component number 1 and component number 4, then it is actually a hyperedge. It's not a simple edge. So hyperedge is a subset of vertices and it's not a simple edge. Any problems? Okay. So I have nodes So V1, V2, V3, V4, and these are the edges E1, E2, E3, right. So if I want to represent the connection between V1 and V4, this is the complete net, right. So this will be represented if I want to represent just the connection between V1 and V4 as the hyper edge. So this is, say, the hyper edge. It is actually this wire that is represented, but in my partitioning problem I represent this hyper edge. Got it? So this hyper edge is actually a subset of the vertices, right. So this is what is a hypergraph, where the vertices are the vertices of the graph and the edges are subset of the vertices itself, right. Okay. No, it's not so. It's just that we are, if you want to visualize it, think that I am representing a net, right, nothing more. It's just that these 2 points are electrically equivalent, right. Okay. So I have the modules and the netlist, and the output is a set of subcircuits which when connected will function as the original circuit, and the terminals required for each subcircuit will also be provided as output. So partitioning can be at different levels. So when I have the complete system and I am partitioning it into a set of PCBs, it's called system level partitioning. When I partition the PCBs into a set of chips, it's called board level partitioning. And when I'm partitioning a chip into subcircuits, which we'll consider, it's called chip level partitioning. Okay. So it's just an example. This circuit is being cut through this line, and I partition it into this subcircuit and this subcircuit. The cut size here is 2, that means the number of wires or nets that is traversing from subcircuit 1 to subcircuit 2 is called the cut, and the cut size here is 2. So one of my objectives is to minimize the cut size between the number of components. Why? Because the time required for a connection within a subcircuit is much lesser than connection between subcircuits. So what we'll do here, we'll study one algorithm and I will define the complete partitioning problem. There are other algorithms as well, but we cannot go through all the algorithms due to time, right? Fine. So given a hypergraph G equals to V comma E, each vertex is a component, each hyperedge a net which represents a connection between 2 components. What is a net? A set of electrically equivalent equipotential points, right? Okay. So each vertex has an area which is represented by AVI, and if I want to estimate the area of a partition, we do a summation over the areas of each of the components within a subcircuit, which is represented by this capital AVI, which is the summation of small av, which is the partition, right? Any questions? Okay. So we also have paths which are called hyperpaths between different components, and another objective is the number of times a path is cut. A single path through the different components, I want to minimize the number of times that is cut to reduce the delay due to partitioning. What is my objective? Objective is to partition this vertex set V into disjoint clusters V1, V2, V3, so that the number of components so that the components in each of these clusters do not overlap. So clusters containing different disjoint components such that the cut size and the maximum length of the path is minimized, right? And the constraints can be the number of terminals in a path always has an upper bound. So, given the area of a subcircuit, I cannot say that I can have innumerable number of terminals. I have a maximum within which I have to keep the terminal count, right? The area of each partition, the number of partitions, the area of each partition is also one thing. The number of partitions that must also be within a specified range. I cannot go on partitioning so that each individual it's the number of partitions is so large that it is difficult to route and right, compact and other things. Okay. So, there are different types of algorithms that are there in partitioning. Some are based on probabilistic, some are deterministic, some are iterative in the sense that I start with a given partition and iteratively improve upon that, like something called simulated annealing, where I go on improving until I get the best solution, and also traversing or bypassing the local minimas for the best solutions, right. And there are group migration type algorithms where this is a deterministic type algorithms, where what I do is I have an initial random partition, say, and I randomly move the components between the partitions to improve them. So, I move a component from here to here, I try to find out whether the cut size gets lower or not, right, and in this way we go on improving. So, we come to the problem formulation. We are given an indirected graph G equals to V comma E, where mod V equals to 2n and E equals to m. So, number of edges is m and number of vertices is twice n, and we are given the cost or weight of each edge. So, the cost of weight of each edge may be the number of connections between two components, right. So, higher is the number of connections between two components, higher is the weight of an edge, okay. And the output is two partitions x and y, so that the total cost is minimized and the partitions are of equal sizes. So, this is the first problem we are going to handle, right. Okay. So, if there would not have been any heuristics used, then what would be the problem? So, for 2n vertices, the number of possible components, the number of possibilities, right, between two partitions, I put it here or here, it will be 2n Cn and the order would be n to the power On. So, for 100 vertices there will be 5 into 10 to the power 28 possibilities, and even if we can say even if we can go through 100 million possibilities per second, it would take 1.59 into 10 to the power 13 years. So, this is the level of complexity of the partitioning problem, right. So, hence we need heuristics. So, we first come to the Kernighan-Lin algorithm. So, we start with an initial Kernighan-Lin algorithm. The problem is this, the problem we are trying to solve is this, not the complete partitioning problem, right. We are given a vertex set containing 2n vertices, an edge set containing m edges, and the cost of the weight of each edge, okay. Okay. And we want to generate two partitions such that the number of vertices are equal and the cut size is minimized, right. So, we come to the algorithm. First we choose a pair of free vertices such that A belongs to partition 1 and B belongs to partition 2. Then we exchange A and B, we exchange such a pair A and B such that the gain through their exchange is the highest. N squared time it will take, right. To find out the gain, it will take n squared time. If this has n edge, we have an initial partition which contains n edges this side, n edges this side. I want to find out the partitions. Because I am given two separate n edges, it takes n squared time. Huh? Acha, what is this? I'm defining gain, right? So some kind of a gain will be maximized, right? So we tentatively exchange and lock them. Why lock them? So that in further such exchanges, these two pairs do not, this pair does not take part, right? So let this gain be AB. So until all pairs are locked, I'll come to this algorithm with an example. Then we unlock all the vertices and we try to find out the step up to which the gain is maximized and actually make those partitions. So we'll continue this algorithm until we get a complete pass where there is no increase in the gain. Now I first define the gain, right? So gain is dA plus dB minus twice dAB, where dA is number of edges that cross the partition, and in A, suppose dA is out A minus in A, where out A is number of edges that cross the partition and in A is number of edges within the partition itself, right. For example, if I consider this node 1, so the number of edges that cross the partition is 1 to 6 and 1 to 5. So out 1 is 2 and number of edges in A in 1 is 1, is the edge 1 to 2, right. So dA, capital DA is 2 minus 1 or 1, sorry, 2 minus 1 or 1, right, okay. And DAB is the weight between A and B. So if I have 1 and 5, then DAB is the weight of 1 and 5, right, okay. So now consider that the weight is 1, right, DAB represents 1. So what I do, I come back to the algorithm, I choose two nodes A and B, I exchange them and I find the gain. So I find out dA plus dB minus twice dAB. So if I take, say, vertex 3 and vertex 5, right. So vertex 3 is 1, out A is 1, 2 and in A is 1. Here vertex 3 is 1, 2, 3 for out 3 and its in is 1. So D of 3 is 2 and D of 3 is 2, no? D of 3 is 2 and D of 5 is 1. So my gain is, so my gain here is how much? My gain here is 2 plus 1 3, because DAB, that means D of 3 5 is 0. There is no connection between AB, between 3 and 5, right, okay. So my right, so I made a mistake. So out of 3 is 2, right, out of 3 is 2. Why? Because there are 3 emanating edges across the partition and 1 edge inside the partition. So out of 3 is 2 and D of, sorry, D of 3 is 2 and D of 5 is 1. So D of gain of 3 comma 5 is 3, okay, and the cut size, if I do this change, the cut size, so this is a mistake here, the cut size becomes 6. Why? Because I have a gain of 3, the cut size reduces to 6, okay, the cut size reduces to 6. And next I exchange, if I exchange 4 and 5, Yes. Oh, why this cut size is 9, you get it? This cut size is 9. 1 2 3 4 5 6 7 8 9. And then when I exchange this, what I actually gain by this GI? I am exchanging 3 and 5 across the partition. So 5 goes to partition, to the left partition, and 3 goes to the right partition, right? So because this is 3, so the number of wires or edges crossing the partition reduces by 3. Got it? Did not get it? Got it? Fine. Then the cut size will be 6, right? Okay. Again I exchange 4 and 5. If I exchange 4 and 5, we will see that the cut size again reduces by 5 more, and the cut size actually becomes this. So, so 5 has come to this side, you see left partition in the right diagram, 5 has come to the left side, 3 has come to the right side, and then I have exchanged 4 and 6, right? 6 has come to the left partition, and 4 has come to the right partition, and after that the cut size has reduced to 1, right? So, but my first pass, this is the least I it's okay, I have locked 4 and 6, but I does not stop the first pass here. I go on exchanging the other vertices as well until the until all my vertices have been locked. So if I don't get a gain, I go on to exchange the vertices that gives me the least loss. Okay, so I come back to the algorithm once. So if I don't get a gain here, I exchange pairs that gives me the least loss until all pairs are locked. So this is within one pass, I am telling. Then I unlock all the vertices. But how much will I actually do? I will find out the number of times which has actually given me the highest gain. So why do I do this? Because let's say I have a situation where G1 and G2 gives me positive gain, G3 gives me negative gain, but G4 again gives me positive gain, so that if I add G1 plus G2 plus G3 plus G4, it gives me a higher gain than just G1 plus G2, even if G3 is negative. So to tackle that thing, we also exchange vertices that gives me lower loss, right? So I go on doing this, but how many passes will I go on through? Until I get a pass where my gain is 0, right? So this is the Kernighan-Lin algorithm. This is called the Kernighan-Lin algorithm. Yes. Right. What is this? Which has the highest gain? No. I'm finding out the highest gain. That is why I take n squared time. That is why I take n squared time to the lowest loss. No, not so. Telling you again. So I take two vertices which gives me the highest gain, exchange them, find the cut size gets lower, then I locked those two. So I have so in each of these partitions, after the first exchange I have n minus 1 vertices. From these n minus 1 vertices in each of these partitions, I take two vertices which gives me the highest gain. Among these n minus 1 vertices from each side which gives me the highest gain, I take such two pairs of vertices. Even if these two pairs does not give me a gain, I select the two vertices which gives me the least loss. So I have no vertex pair that gives me gain. Then I select vertex pairs which gives me the least loss. and go on with that exchange and lock it. Least loss, that means I have a gain in cut size. Instead of getting a lower cut size after the exchange, I have an increase in cut size.
So, like, if you have a -1 and -3, which is the least loss?
-1, least loss.
Exceeds the
So -1 means my cut size gets increased by 1, right? So why do I do that? I just told you. Even if this gives me -1, after I have made this partition, I can get a vertex pair which again gives me good gain after this, after I have already done this partition. And then I actually take up to that step G1, G2, G3, G4, even if there is a loss in between or 2 losses in between, n number of losses in between, I find out up to the steps which gives me the highest gain. Okay, right. So the complexity of this algorithm, yes, right, yes, no, but the problem is, yes, according to the algorithm that should be done. This is an example. So does before 3 and 5 is partition, before 3 and 5 are exchanged, does that still give 5? No, na? Only after 3 and 5 are exchanged, this 4 and 6 gives me such a high gain, isn't it? So that's why this is done. Not. No, we won't know that. We won't know, not random. I have n edges on this side, n edges on this side. I take up n squared time to find out within each edge what is the gain, right? For each pair, what is the gain? I take n squared time and find out.
So when we got this 3,5, we have already made those n squared combinations.
Right.
And then after finding 3,5, we again do the n squared combination to find the next one.
Yes. No. N squared is done. And not n minus 1. I have all the. No. We require. We require n minus 1 square.
So then, as going by the algorithm, we say that find the number of steps required, exchanges required, so that G is maximized.
Yes.
Now, once G is maximized, and we just terminate when G is 0, right?
No. So this, when G is maximized, this is one pass. In our example, we don't require any more passes, but this whole thing can be done again. So given this partition, over this partition again I do an n square, find out the highest of these pairs. So I have unlocked all the pairs. What I was doing here is I was locking, and from the remaining things I was again selecting pairs. Then after one pass I have completely unlocked. Up to a step I have actually checked out the partitions, and after that I have not done the partitions. So given this partition, if this was a fresh partition here, I again iteratively do the same thing. From the n square I find out the best and do it until I have a complete pass where I don't get any gain. No more questions please after the class. Okay, so Kernighan-Lin algorithm takes time proportional to C n square. So initial computation takes O(n) time of the D's of the D's. Then within a pass, computation of gain takes O(n) square, and the number of passes is usually small, which actually gives me that C, total number of passes, right? So it's C n cube on the whole, right? Drawbacks of this algorithm: considers unit vertex weights only, right? Not applicable to hypergraphs. That means it cannot be considered to big nets. So partition sizes have to be pre-specified, high time complexity. So there are many other algorithms that that has been done. One industry standard that was used till recently was fiducial mathesis. Probably it's now also used. So it allows hypergraphs. It allows, so I don't have to do an exchange, but I can just move a component from this partition to that partition. So it also allows unbalanced partitions, right? So that is also required. Now I need not have a partition where all partitions contains equal number of vertices, right? Okay, so then there are other algorithms. You can study Goldberg and Burstyn and simulated annealing as well, right? But we won't go into all those algorithms, right? So now we come to rather the floor planning phase. So the outcome of the partitioning phase gives me a set of blocks, the area of each block, possible shapes of each block, number of terminals in each block, and the net list specifying the connection between blocks. Okay. Now if I have a fixed block, so what is a fixed block? Where the layout, the circuit layout within the block is completely known. So therefore I exactly know what will be the dimension of the block, right, its shape. And flexible block, where the dimensions can be varied within a range. So if I consider only rectangular blocks, so I have a lower bound and upper bound of the aspect ratios that I can have, right, that I can maneuver with. Okay. So here I have a few connected problems. One is that of floor planning, chip planning, then floor planning, placement, and pin assignment. What is chip planning? Rather, I come to placement first. What is placement? I have been given a set of fixed blocks. I know the exact dimensions of the blocks. I need to place those blocks on the floor area, right? This is the placement problem. The floor planning problem is also a placement problem. It's just terminology. The difference, I have fixed and flexible blocks as well, right? So placement of fixed and flexible blocks together is a floor planning problem. So placement problem is a sub problem of the floor planning problem. Then I come to chip planning. Chip planning is I also try to optimize the interconnection plan. Along with the floor plan, if I also try to optimize the interconnection plan, I consider it the chip planning problem. Then I have the pin assignment problem. I know the number of terminals, but where should the terminals be placed? What will be the pins? What will be the interconnections? So so the sorted order of an order of the pins to be placed on the side of the blocks gives me the pin assignment problem. So I first come to the floor planning problem. So the input to the floor planning problem is a set of blocks, both fixed and flexible, right? The pin locations of the fixed blocks are known, and I know the net list. What are my requirements? Find the locations of each block so that no two blocks overlap, fine, and determine the shapes also of the flexible blocks. Objectives is to minimize the area and reduce the net length for critical nets. What is the critical net? Where I have a bound on the time which I can take for the interconnection, right? So the time for the net cannot be more than this. So the length of the net must be smaller than this, right? And the pin assignment problem, the input is the placement of the blocks. I know the placement of the blocks, the number of pins in each block, possibly an ordering, and a net list to determine the pin locations on the blocks and to minimize the net length. The objectives are to minimize the net length. See, these problems are actually interconnected. I cannot optimize it fully until I take the complete problem together. But I have to make a divide and conquer approach to it's because it's so complex, because the interconnection, see, the routing and placement and partitioning, they are all linked together. The best partition, the best placement for the most optimal routing cannot be three separate problems actually, but I have to do it to tackle the problem. Okay. So what is a slicing floor plan? A floor plan which can be, in which a rectangular area can be recursively cut horizontally or vertically to get the floor plan, is a sliceable floor plan. Okay. So here I can recursively cut it, this, then this, then this, then this, then this, right? Okay. And a non-sliceable floor plan, I cannot slice it recursively into, I cannot, I don't have in this complete, given this complete area, I cannot have one complete line that cuts through recursively, right? A hierarchical floor plan. So here I have a set of components and I hierarchically partition that. So the leaf nodes define individual components and the internal nodes gives me composite components. So I now come to floor planning algorithms. Different kinds of algorithms: rectangular dual graph approach, hierarchical approach, simulated annealing. There are numerous others also. You can see Naveed Sherwani's book to have a complete list of the different approaches that you can get, but I cannot go through all the problems now, obviously, right. So in the rectangular dual approach, the outcome of the partitioning algorithms is given by a graph. Floor plans can be obtained by converting the graph into its rectangular dual. So what is the dual of a graph? Given a graph G equals to V comma E, right? So given a graph, I'll have its dual. So its dual will be the vertices of its dual graph. I am considering its dual graph. The vertices of this dual graph will be the faces of this graph. What is the face? What is the, what is the face of a graph? The face of a graph is, so if I have a graph like this, so these two are faces, right? F1 and F2 are faces. So these will be vertices, and if the faces have an adjacent edge, that means F1 and F2 share an edge E, this one is E, then its dual will have an edge between F1 and F2. So in its dual, F1 will be a vertex and F2 will be a vertex, and there will be an edge between F1 and F2 due to E1 and E2 here, right? So if I have F2 and here and F3, then there will be a connection between F1, F2 and F3. Okay. Yeah, that's what I was drawing. Right, this is the graph. So this one is F1, this one is F2, and this one is F3, say. So F1 and F2 will have a connection, F1 and F3 will have a connection, F3 and F2 will also have a connection. Okay. the rectangular dual so the rectangular, in its rectangular dual, each vertex will be a distinct rectangle and each edge, the corresponding rectangles, in there will be a rectangle, there will be an edge if the rectangles are adjacent. So if this is on the opposite problem, if this is a rectangular floor plan, right, if this is a rectangular floor plan, then I have a graph corresponding to this, like this below. So we assume a rectangular floor plan which contains no cross junctions. That means, what is a cross junction? A cross junction is a junction like this. So cross junctions, if we have, we change it to a T junction like this. This is a T junction. Right. So in this, a rectangular floor plan will have a planar triangulated graph. So we first need to know what is a planar graph. A planar graph is just a graph which can be drawn on a plane without two edges crossing, is a planar graph. What's defining a triangulated graph? If a graph has a cycle V1, E1, V2, E2, V3, E3, V4, V4, say a cycle of length 4, in such a cycle, I will have a chord for each cycle of length at least 3. So sorry, greater than 3. So there will be a chord. So chord will not be, chord means an edge which is not part of the cycle but is part of the edge set of the graph. A chord is an edge which is not part of the cycle but is a part of the edge set of the graph and connects two vertices within the cycle. Correct? So there will be a chord for each cycle of length greater than 3. So that is called a triangulated graph. So a chordal graph, this is called a chordal graph. A chordal graph is also called a triangulated graph. Now we consider planar triangulated graphs. So we say that a rectangular floor plan will always have a planar triangulated graph as dual. So every dual graph of a rectangular floor plan is a planar triangulated graph. We consider all cross junctions by transform all cross junctions by T junctions. For such a floor plan, I have a graph like this. But not every planar triangulated graph will have a floor plan, right? So sorry, 1 minute. So this 2 and 3 is this should be 2 and 3 here. So there is a mistake on my part, right? Okay. However, not every planar triangulated graph will have a rectangular floor plan. For example, this has a complex triangle. That means this, and this forms a complex triangle, and I cannot have a rectangular dual for this. You understand why? Because see, for this 1, 2, 3, 4, whenever they are adjacent, I draw an edge in between. So 1, 2, 3, 4 are vertices, and there is a connection between 1 and 4. There is a connection between 2 and 3. There is a connection between 1 and 2, and there is a connection between 4 and 3. Right? Because all of them are adjacent, neighboring tiles. 2 and 4, 2 and 4. 2 and 4 is also connected, but okay, but probably because we have changed this cross connection to a T connection. We don't draw that. That's the only reason that I can give you at this point, or I'll tell you afterwards, right? At this point in time I don't know, right? No, that's probably not wrong. So, but over here, when I have a complex triangle, I cannot draw such. With these 4 vertices, I cannot have such. You got it? Why? So, this is adjacent. So, 1, 2, 3, 4. I cannot have all these 4 adjacent to each other, and I cannot have a rectangular floor plan corresponding to this complex triangle. Complex triangle with these 4 vertices, I cannot have a rectangular dual, because I cannot maintain that adjacency relationship. Whenever there is an edge, those 2 must be adjacent. So, suppose this vertex represents this. Sorry. So, this vertex represents this rectangle. This vertex represents this, and this vertex represents this. So, these are adjacent, but because this node in between needs to be adjacent to this all 3, I cannot keep this block adjacent to this above block. Got it? So, I cannot have a rectangular floor plan corresponding to this complex triangle. What is the solution? The solution is that I insert an edge insert a new vertex in between. That may be a vacant tile, but I insert an edge in between to maintain this adjacency relationship. To break this complex adjacency relationship and be able to draw a rectangular floor plan. Select a minimum set E of edges such that each complex triangle has at least one edge in E. A vertex can be added to each edge E to eliminate all complex triangles. So, I need to break these complex triangles. So, the weighted complex triangle elimination problem is NP complete again. Fine. Okay. Now, we come to the hierarchical approach. So, in that hierarchical approach, it is a divide and conquer approach. I take small subcomponents, find out all enumerations of all floor plans with that small components, find out the optimum floor plan for that small components, and then group them into bigger components to find out the optimal floor plan for that higher bigger component, right. So, that remember that hierarchical tree here. So, I group them starting from this, I group them like this and then go on developing higher, right. Okay. So, it is a widely used approach. At each level of hierarchy, only a small number of rectangles are considered. A small set and all possible floor plans, that is not and obviously. After, so I find out the optimal configuration for 3 modules and then I merge them together. So, the possible different floor plans are 1, 2 and 3 here, find out the optimal and then merge them. So, the number of possible floor plans increases exponentially as the number of blocks at each level increases. So, if D is 2, then I have only this many. If D is 3, I can have this many possible different floor plans. So, if D is 6 and D is 10, we can imagine, right. So, hierarchical approach can be in both top down and bottom up ways. So, hierarchical approach works best bottom up, right. So, the modules having very high connectivity are clustered together such that the number of modules in each cluster should be lesser than some given upper limit, because we know what are the problems if the number of components become higher and higher, right. So, an optimal floor plan for each of these clusters is determined by exhaustive enumeration. Within that, we do not apply any heuristics. we try to take all things into consideration, the different shapes that can be given to each of the modules, the minimization of interconnection length of the nets in between, everything. So we try to generate the exact enumeration. Clustered these merged modules into larger for higher level processing. Then at the higher level processing, again these becomes individual components, and again we cluster them, right? So in the greedy procedure, so if the edges represent weights, what happened? If the edges represent weights, we sort them in terms of their weights. The heaviest edge is chosen, and two modules of the edge of the different edges are clustered together greedily, right? Again the restriction is the same. At the next higher level, the clusters are merged and the edges are summed up to find out the edge weights for the next higher level. The edges here are summed up. So I have a component, for that I sum up their edge weights to find out the weight for the next higher level. The problem, there can be some lightweight edges which may be chosen at which can be chosen at a higher level of hierarchy, resulting in adjacency of two clusters of incompatible sizes. That means there is a lightweight edge and I have a single component, small one. I don't consider it. I greedily consider higher weight edges and go on joining them to find larger components. This lightweight edge is left with. So I have come up with a very big component and a very small component because the edge between them is very lightweight, right? So this is the problem. Solution: arbitrarily assign a small cluster to a neighboring cluster when their sizes will be too small for processing at the higher level. So with the greedy approach, what we also now consider is what are the sizes of the different components. If it becomes infeasible, well, the edge is very lightweight, fine, but the component sizes are so incompatible that I need to join them at this level itself. I cannot take up to a high level of hierarchy anymore, right? This is the solution. So the problem is here. So the problem here is this one. I have a big component C with a small component E. The solution is here. So I have joined it with D at this level itself, so I don't get it here anymore. I don't get a floor plan like this, right? So the main thing is here is because they are incompatible, I get large vacant spaces which I don't want. Here I have this many vacant spaces here which I don't want, so I have reduced the vacant space here. Got it? Right. So how do I estimate the cost of a floor plan? Right. So the estimate is done based on the interconnections and the area of the floor plan. So the area is estimated because the dimensions of each cluster that is passed in the bottom of clustering is known. The area of a particular choice, the area for a particular choice can be computed from its component floor plan, candidate floor plan, right? And the cost can be estimated by summing up the edge weights multiplied by the distance of the centers of the clusters, right? So the edge weight between the clusters I know, the edge weights, and the distance also I know. So what I want to minimize is the total cost of the interconnect, right? So that the summation of that will give me the cost of the floor plan. So the distance and the weight both I need to consider. I need to minimize that. Okay. So top down approach is the other way around. I have the complete component and I partition them to find out the floor plan for each of them from a top down at the top, from the top down level, right? So I stop here. with introduction, partitioning and floor planning. My friend Subrat, he will be taking up from the next placement, routing, etc. Thank you.